Hello, this is Jack Jackson. We're now going to prove the things that we have discovered about kites in the last video. And the key thing about kites is that when you look at the major diagonal, it breaks it into two congruent triangles with a reflection. And that's really kind of the key piece. And that class of quadrilaterals with a reflection uh, two triangles that are congruent with reflection is going to exist in all the different geometries we've discovered. And when it has that property, it has all the main properties of a kite. It is a kite and has the properties of a kite. So all of the proofs that we're going to be looking at sort of pass through this part where we make those two triangles congruent. We either they're given that or we prove that. Now the way we do that could be rely on any of the triangle congruence properties we've studied, the side angle side postulate, angle side angle congruence theorem, side 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 congruence theorem, angle angle side congruence theorem. And so we can do those. If we can avoid the angle angle side congruence theorem, we know the rest of those are true in spherical geometry. They're all true in Euclidean geometry, and they're all true in hyperbolic geometry as well. So if we can avoid using things that aren't true in those other geometries, we can prove the same properties for hyperbolic and spherical geometry that we have with Euclidean geometry. So if you're in a high school class and you're not studying about these non-Euclidean geometries, just ignore the stuff that I'm saying about these other geometries. So here we have triangle A, B, C, D, and it's a kite. So it has two pair of congruent sides that are adjacent, two non-overlapping or two disjoint pairs. So AD is congruent to AB and DC is congruent to BC. That's the definition of the kite. And we're going to look at the properties of the kite, including some properties that we have of its diagonal. Okay, so if it is a kite, we found that it has these properties here. First of all, it has the property shared by all quadrilaterals because it's a quadrilateral, four sides, four vertices. In Euclidean geometry, the sum of the interior angles adds up to 2 pi radians or 360 degrees, and so forth. The minor diagonal, which is the one here, DB, is going to make two isosceles triangles, ADB and DCB. It has, those are not necessarily congruent. The major diagonal and the sides make a pair of congruent triangles, and that's really one of our key things, that triangle ABC is congruent to triangle ADC. By the way, the order you say these things does matter because this is the congruence with a reflection, which is what we have here. There's a pair of opposite congruent interior angles, angles B and angles D. That's angles ABC. ABC, big angle right here, and ADC, big angle here. The line containing the major diagonal, so the line AC in this picture, contains the bisectors of interior angles. So that means your angles A or DAC and BAC are congruent, bisecting here, and also same thing on this end. Okay, what else do we have? The line containing the major diagonal is a perpendicular bisector of the minor diagonal. So if we take this line through A through C, it's going to intersect the minor diagonal. That point right there is the midpoint, and these are all right angles right there, perpendicular bisector. And when we look at these four little triangles involved here, where we have the two diagonals and the sides, these two right here, triangle AD, call that X, is congruent to triangle ABX, and those are congruent right triangles. And these two over here are congruent right triangles as well. Angle CXD is congruent to triangle CXD is congruent to triangle CXB. And then once again, it has reflective symmetry about the line containing A and C. So those are properties that we have. It's also true that these are some following necessary and sufficient conditions for a kite. In other words, the following are equivalent. If you have any one of these conditions A through G, you have all of them. So the first one is that quadrilateral ABCD is a kite, specifically with AB equal to AD and BC equal to BD. I could have phrased that as line segment AB congruent to line segment AD and line segment BC congruent to line segment BD. The diagonal BC and the sides form a pair of not necessarily congruent isosceles triangles, BAD and BCD. If those two triangles are there, then you get all these other properties as well. The major property C, the major diagonal of sides form a pair of congruent triangles. ABC is congruent to triangle ADC. The line containing the diagonal AC bisects the interior angles DAB and angle DCB. The line containing the diagonal AC is perpendicular bisector to the minor diagonal. The line containing the diagonal AC is a perpendicular bisector of the minor diagonal BD. The line containing the major diagonal, the minor diagonal, and the sides form two pair of congruent right triangles. And then quad ABCD has reflected symmetry. So if it has any one of these sets of properties A through G, it has all of them. And the key is this one right here, part C. So everything's going to go by way of C. So we're going to prove this theorem in two parts. Okay, if we show that part C, if we got the two congruent triangles, we get all these other things. So we're going to show that C implies each of A, B, D, E, F, and G. And then for part 2, we're going to start with each one of these A, B, D, E, F, and G and show that we can get from them to C. And by the way, once we've done that, then we've proved all the stuff in part 1 as well. Okay, so here's the proof. So again, the first half we're going to start with the two congruent triangles. So for a while we're going to know that part C is true, that the triangle ABC is congruent to triangle ADC. Okay, well, if we start with that, by definition, congruent triangles, corresponding parts of congruent triangles are congruent, we get line segment AB is congruent to line segment AD, line segment BC is congruent to line segment DC, and so that's a kite by definition. So condition C implies condition A. Furthermore, once we have that, if we draw the minor diagonal, we see that these have to be isosceles triangles because we've got these sides congruent. So condition C is going to imply condition B as well. Now, if we go a little bit further, properties of congruent triangles tell us that we have congruent angles as well. So notice that we get a pair of congruent angles here at B and D. Okay, and then look at the major diagonal. Because of these two triangles being congruent, these angles here, BCA and DCA, are congruent. So we have an angle bisector at that end. And DAC, that angle is congruent to BAC. So we have angle bisectors at both ends. Therefore, condition C implies condition D. Next, construct the minor diagonal as well after we first done the part above. Now what do we know? Well, again, if we have these two triangles congruent, let's look at what's going on here. Let's let this point X be the point of intersection of the line containing AC and the line AC, right? Not just the diagonal, but the full line. So that intersection point may be in the interior of the, well, it's a kite, or the exterior of the kite. Okay. Now, either way, we've got some right triangles here. Let's say, look at the blue one here. ABX and ADX are both well, we haven't proved that they're right triangles yet, but we do have two triangles there that we're going to show that they're right triangles. Okay. Now, what we're going to do is now show that they are congruent to each other. Well, how do we do that? Let's see. We've already shown that these two big triangles are congruent, so that means that this angle here, BAX, is congruent to DAX. So these two angles right here are congruent. Um, and then these two sides are congruent, and then the side AX is congruent to itself. So that's enough for side angle side. So the side angle side postulate tells us that this triangle is congruent to that one. Okay, and we get this exact same argument here on the other side. And it doesn't matter if we're looking at this picture, looking at the big triangle here and versus the big triangle here, or these two little right triangles here. Now we haven't proved they're right triangles yet, so let's do that. Once you know that these two triangles are congruent to each other, that is ABX is congruent to ADX, that means that corresponding parts of congruent triangles are congruent, so DX is congruent to BX, and we see that this X is the midpoint of line segment BD, the midpoint of the minor diagonal. So we know the major diagonal, or at least the line containing the major diagonal, bisects the minor diagonal. Furthermore, we know that these two triangles are congruent, so the angles at X, that is the angle BXA, is congruent to angle DXA right here. And since those are congruent and they form a linear pair, they are supplementary and congruent, therefore they're both right angles. So we've proved that the line containing the major diagonal is a perpendicular bisector of the minor diagonal. It's not quite true to say that the major diagonal is a perpendicular bisector of the minor diagonal because they may not actually intersect in the concave case like this. Okay, so what have we done? We've shown that condition C implies D, condition C implies condition F, and condition C implies condition E. So what is a reflection? Well, reflection is a linear transformation that maps points. It fixes the points on the mirror line. So if we know that if we have reflect over, or we want to show that this triangle on the top is a reflection of the one on the bottom, well, it's going to fix A and C, excuse me. So all we really have to do is show that B gets mapped to D. Well, what does it mean to be a reflection? It means that when you connect up the image, pre-image and image points, B and D in this case, that the line segment from B to D is perpendicularly bisected by the mirror line. Well, that's exactly what we've already just proved. So in fact, condition C implies condition E, which implies condition G. So we've shown that in each case, condition C implies each of the other conditions. So if you start with this one, you get all these others. Now we reverse it and show that if we take any one of these others, we prove this one. Those are the converses of what we just did. Okay, so let's take it one at a time. Let's start with condition A. We're given quadrilateral ABCD as a kite. By definition of a kite, it has two disjoint pair of consecutive congruent sides. So that is AB is congruent to AD, BC is congruent to DC. Well, AC, the diagonal, major diagonal, is congruent to itself, so now we have enough to use side, 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 congruent triangle congruence theorem to show that the two triangles are congruent, so conditional A implies condition C. Specifically, when I say the two triangles are congruent, specifically triangle ABC is congruent to triangle ADC, congruent with a reflection. Now, what if we start with condition B? Condition B says we're given the minor diagonal and the sides form a pair of not necessarily congruent isosceles triangles. Well, by definition of isosceles triangles, that means AB is congruent to AD, BC is congruent to DC, and now we're back to condition A, so condition B implies condition A, which we already showed implies condition C. So condition B implies condition C. All right, how about D? Starting condition D. What's condition D? We're given a line containing a diagonal AC bisects the interior angles. So we've got it. We're bisecting these angles right here. Okay, on both ends. I guess technically you're bisecting the angle on the outside here. The outside here you're bisecting it, but you can get from that to bisecting the one bisecting this. So these two are congruent as well. So either way, we're going to eventually get what? Angle, side, angle, because AD is congruent to itself. So angle, side, angle now is enough to make these two triangles congruent. So condition D implies condition C. So notice every time we're disproving these two triangles are congruent, but the way we do it depends on what we're given. We might be using the, one time we use side, side, side. Another time we used angle, side, angle. Okay. So far we have condition A, B, and D each imply condition C. They imply we have these congruent triangles. How about if we have condition E? What's condition E? We're given the line containing the diagonal AC is a perpendicular bisector of the minor diagonal. So this line AC perpendicularly bisects the minor diagonal BD. So what do we know? We know that BD and BX and DX are congruent. We know that these are both right angles here, BXA and DXA. Well, AX is congruent to itself. That makes this triangle and this triangle up here congruent by this side angle side postulate. And similarly, we get the triangle BXC is congruent to triangle DXC, again by side angle side. Okay, so condition E implies condition A, that we have, so then from there, what do we know? These triangles are congruent. That makes the two, well, the hypotenuse here and the hypotenuse here are congruent. Two blue sides, AB is congruent to AD. Since these two triangles are congruent, since these two are congruent, BC is congruent to DC. And now we know it's a kite, and we already showed that was condition A, and condition A we already showed is enough to prove condition C. So condition E implies condition A, which implies condition C. What if we start with condition F? We're given a line containing the major diagonal and the minor diagonal forms two pair of congruent right triangles. Well, that's basically where we were. If we know that these two are congruent right triangles, that gets these two congruent, and these two are congruent to each other. Triangle BXC is congruent to triangle DXC. Again, that makes these two sides here, and we're back to A again, which is enough to get C congruent. Okay. Starting with condition G, we're given a quadrilateral has reflective symmetry. Again, what does reflective symmetry mean? Well, it means that we reflect over this line AC. A and C are fixed, but B is mapped to D, and it's done in such, and D is mapped back to B, such that what happens, this line segment from B to D, pre-image to image, is perpendicularly bisected by the other one. Well, that's just says that condition G gets us back to condition E, which we've already shown gets us to condition C. So notice in every case we're going by way of a congruent triangles. Up here in part 1 we started with congruent triangles with a reflection and showed that we could get all the other properties. Down here we took each set of these properties and showed that we could get our congruent triangles. So all these conditions are equivalent to each other, and notice that collectively they list all the properties of a kite included in section 1 of the theorem, so section 1 of the theorem has also been proved. Furthermore, notice that we only use propositions that are true in Euclidean, hyperbolic, and spherical geometries, so this theorem is valid in all three of these geometries, even though the illustrations were only for Euclidean geometry. So we have proved the properties of a kite theorem. There again, there are the properties, some more, and that these are equivalent to each other.